There we go, a mic. uh, all right, hello. Hello, hello, hello. Page will be on here. We're gonna be on page. 85. Okay. There we go. Let's move. Let's slide over to page 85. Okay. Got this here. Then we got this. Let's do that. This and this. Okay. Go. Okay. There we are. Hello, hello, hello. All right. Don't know why it shows that, but it's really weird. Alrighty. Hey, how's it going? How we doing, Julio? Yeah, I'm doing pretty good. Doing pretty good, my friend. I hope hopefully you had a nice couple of days just to relax and, you know, chill out a little bit. So, how about yourself there? How we did you end up doing anything the past couple days or no? Cool. Just work? Fair enough. Me too. Just work. Just working. Tuesdays are Tuesdays are game night, so did a little game night yesterday, and came back pretty early. So, all right. I see some other people here in the chat. That's good. That's good. Okay. We'll get started here in about a minute or so. Maybe we'll let one or two more people hopefully will show up, and then we'll go ahead and get going. Okay. Hey, Brenton, how are you? Good, good. Hopefully you had a nice. Yeah, I'm pretty good. I'm pretty good. It's been a nice, relaxing couple of days, just working and having game night. So yeah, not too bad. Not too bad. Not too bad at all. Hopefully you didn't have a. Hopefully you didn't have a eventful couple of days. Hopefully you had a chill couple of days. All right. Cool. 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 All right. Um. Okay. I think we've been about a minute or two, so we gotta get going here, and yeah, we'll get started. Okay. So let's do this. Okay. Okay, let's get started today. Welcome back to Wednesday, end of the week time today. So today we're going to be talking about chapter 2. Last time we talked about the syllabus in chapter 1. Today we're going to be talking about chapter 2. We're going to get started with chapter 2. Now chapter 2 deals with everybody's favorite concept in mathematics. It is the best concept that you've ever seen in math in the history of mankind. All right. I know that everybody is like totally in love with this. Chapter 2 is all about fractions. I know the love for fractions is quite high amongst you guys. I think everybody likes fractions in some form or fashion. Okay. Um. Uh. Yeah. Maybe not. All right. So we're going to explore about fractions here in this chapter. We're not going to go through the whole chapter here today. What we may end up doing here is we may end up just doing the first two, three. Yeah, we may end up just doing the first three sections here, and then I would reserve the last section there for next time. So again, because I did chapter 1 kind of all at once last time, there's one more reason why I do chapter 1 all at once, and that is to be ahead of the pace there for reasons later on. So uh, if we work ahead, then tougher material I can spend a little bit more time on later on in these next 8 weeks, so that way I can go slower over that over anything else. Okay. All right. So for fractions here, let's talk about the basics of fractions here. That's what this first part is talking about. So the basics of fractions here is, um, let's talk about basics of fractions. Okay, so the first and foremost thing is the parts of the fraction. Of course, as we know here, we have a top number, we have a bottom number, or again, we call this the numerator, and on the bottom here we have a denominator. Okay, so we have a numerator over denominator. That's going to be the basic of fractions. Again, just to kind of reiterate here, Oftentimes, you may see me interchange numerator and denominator in terms of saying, let's say the numerator here is the top number. So sometimes I may say top, and the denominator equals the bottom number. Okay, so if you hear me say top and bottom, again, that's in reference to numerator and denominator here, respectively. Again, sometimes I just interchange just to ease of use. Okay, so again, what is a type of fraction here that you've probably seen before in the past? This shouldn't be anything brand new to most of you. If you've seen it at least once in your life, then that's fine. So you could have, say, 1 over 3, or again, you could have, say, let's pick another fraction here, um, 5 over 11. Okay, things like that that are fractions. You could have a fraction that looks like this, like 17 over 4. Okay, something like that. These are all different. These are all types of fractions that we'll basically see uh, in this particular chapter, and pretty much in throughout the course of the book. Now, let's talk about the next part here, at least here in this section. Let's talk about type of fractions, okay? So while we have a numerator and denominator, let's talk about types of fractions here in this particular case. Okay, so we're going to encounter two types of fractions here. We're going to encounter a proper fraction. Okay, and what is a proper fraction? A proper fraction just means that the numerator is less than the denominator. Okay, so if the top number is less than the bottom number, then that is a proper fraction. So examples of this is basically these first two ones, like 1 over 3 and 5 over 11. Okay, these would be examples of proper fractions. And then we also have on the other side here, we have improper fractions. Now, for the purposes of what we're going to be doing here in this class anyway, improper fractions are going to be also very important as well. Now let's talk about the definition of improper fractions here. Improper fractions is where, and I'm going to actually write this out, where the numerator is bigger than or equal to the denominator. So where the numerator is bigger than or equal to the denominator. Now, what's an example of this? Well, 17 over 4 would qualify as an improper fraction because, as you see, the top number here of 17 is larger than the bottom number here of 4. One more example of an improper fraction will be this. That will be 3 over 3. This is also an example of an improper fraction. Okay, again, why do I stress this one in particular? Well, that's strictly because of the fact that we have bigger than or equal to in this particular case. Okay, so 17/4 and let's say 3/3, again, can be represented that way. Okay, all right. Okay, so we're going to come back to improper fractions here momentarily, but before we do, are there any questions so far from you guys? Okay, so no questions here. We'll go ahead and move forward. Okay, now um, let's talk about why improper fractions here are going to be very important for what we're going to be doing here in this chapter. So the next topic we're going to talk about here is going to directly relate to improper fractions. And so in this section here, we're also going to introduce the concept of, let's get that going here. We're going to talk about the concept of mixed numbers. Now, oftentimes on the homework, it may ask you to go ahead and put in your answer in terms of a mixed number. So the question is, what is a mixed number? What does a mixed number look like? Well, a mixed number is going to look like this. You have a whole number part, we'll call it, in this case, 3, and you have a fractional part right next to it, which could be like 1/16. All right, so 3 and 1/16, that would be, say, the fractional part, just like so. So if you have like 2 1/8, like a 2 1/8 drill bit, okay, that's a mixed number at the end of the day if you're trying to say that out. So an example would be like 3 and the 16th or something like that. But what's more important here is we need to take these mixed numbers here and we need to be able to convert them over into improper fractions and vice versa. So we're going to take a look at that next here in this section. Now, I know this is a lot of information here, but the reason why I'm stating this is because this really helps us set up for the last 3 sections if we know how to do this specific part. So I'm going to kind of stress this part here, and we'll go slow over some examples here for sure. So let's start off with mixed numbers to improper fractions. So for us to do certain calculations, we want to go ahead and do this here to change mixed numbers to improper fractions. So the way it's going to go is, let's go ahead and take a look at our formula here, because there is a specific formula to this. Okay, so I'm going to get out the paint tool here. Okay, so the way it's going to work is, actually, let me go ahead and state it with this, and then we'll just try it out. Remember, in this case here, we have a whole number. We'll call that big A. And we have a fraction here, just like we have a B and a C. Now, if we want to convert this mixed number into an improper fraction here in this particular case, then what we're going to be doing here is we're going to take the whole number, okay, of big A. We're going to multiply that by C. Again, we're going to do A times C first. We add that to B after we multiplied. And then we want to keep our denominator here of C. Okay? So this is going to be our little formula here for us to go ahead and convert it from one mixed number here into an improper fraction. Okay. Now, let's take a look here and see let's take a look at some examples here, and let's see how we can find those out. Kind of the good old manual way here. All right. So let's start off with 3 2/5, okay? And so we just want to convert 3 2/5 into an improper fraction. So to go ahead and do that, let's follow the formula here with actual numbers this time. So A here would be 3. So we're going to take 3, multiply it by the denominator, which is going to be 5. And then we're going to add that to the numerator of 2. And put that all over 5. So here in this case, we get 15. 3 times 5 is 15, plus 2 over 5. And then if we put that together finally, we get our answer of 17 over 5. Okay? So there we go. We got our improper fraction here. Again, changing from a mixed number to an improper fraction. So we got 17 over 5 here as our result. All right, any questions about that so far? I'm going to do another example here, but just showing off here, so. No. Okay. Okay, let's look at another, and then you guys can help me out with this one. All right. How about 5 and 9/10? How about 5 and 9/10? What's that equal to as an improper fraction? 5 and 9/10. Go ahead and type that answer in the chat there once you got it. Okay. Says 59 over 10. Anybody else? Okay. All right. Okay. So, all right. Good. That's correct. 59 over 10 is correct. So again, we're going to take the 5 times the 10, add the 9, put that all over 10. 5 times 10 is 50, plus 9, 59 over 10. Good. So that's correct there. Good. Change it to a better looking 5 though. There we go. Slightly better. All right. Okay. So that's how we can convert, again, mixed numbers into improper fractions. And what we're going to be using this for specifically is to make problems significantly easier if we need to do any operations with them. So certainly, certainly this is definitely one that's high on the list. Okay, but of course, with these two examples, we're going to need to go backwards as well. Okay, so let's go ahead and talk about that part here. So here we're going to go from improper fraction to mixed number. So let's do an example here, and then we'll go ahead and see how we're going to approach this, at least in this class, of converting an improper fraction right back to a mixed number. As I mentioned here before, some problems will require you to put in a mixed number as your final result. So again, I just want to kind of stress that and be like, okay, we need to kind of go backwards here once we're done doing some sort of calculation, then wanting to put it in the correct format that it asks for. All right, so the way for us to do that here is, let's do an example with this one. All right, so let's do 103 over 8. So 103 over 8. So we're given an improper fraction here, and we're just given the fact is like, how do we find what what the mixed number is going to be? So here's what we do. So the trick is to use basic division and the remainder. So we're going to use the remainder after doing some basic division and put it all together all in one shot. Okay. So the way it goes is that it goes like this. Okay. I want to get this right here. So it'll look like this here. It'll be the quotient, and then it'll be the remainder, and it will be the denominator. I guess I'll replace quotient with answer. Maybe that's a bit easier. I don't know, some people are kind of on the fence about that, but okay. So let's show this off here and how it works, at least for this particular example. So I'm just going to do straight up division. 103 divided by 8. So again, just doing basic division here. 8 goes into 10 once. Okay, so subtract 8. Do 2, bring down the 3. 8 goes into 23 twice. So that's going to be, again, 16. And here we get a remainder of 7. So the way we put this together here is, this is our answer up here, our quotient, okay, of 12. So this is going to be representative of our whole number. So our whole number on the outside here is going to be 12. The remainder here will be the numerator of our fraction. So this 7 is going to go right here as part of our fraction. And then what we divided by was we divided by 8. So since we divided by 8, that's going to be our denominator right here. So we're just putting those pieces here together to essentially put together our mixed number here. So our final answer here is 12 and 7/8. Any questions about that? I'm going to try another one, but okay. Let's try another one though. No? Okay. Jeez. Too much gas today. All right. Gotta stop that. All right. Let's do the next one here. Let's try. Sure. Let's try how about 19 over 7? Write that as a mixed number, 19 over 7. I'll give you guys a try here. So 19 over 7. Okay, that's correct. Nice job. So 2 and 5/7 is the correct answer. Again, find out how many times 7 goes into 19. That's twice. And that's with the remainder of 5. Okay. All right, so it isn't that bad to do. Again, one of the easiest ways that you can quickly do these problems here is, again, you could use the calculator here. So you could do 19 divided by 7, take the whole number that you see there, which is 2, and then take 2 times 7, which is the 14, then take 19 minus 14, get 5. So you could use your calculator as well, just have to do it in a few steps, and you'll get the same result regardless. Okay, especially with larger numbers, it's easier to use the calculator and kind of ignore the decimal part, then work with the rest. Okay. All right. Okay. Let's go ahead and put in the next part here. Alrighty. So a few things we have to talk about when it comes to basics of fractions, and then once we get all these basics out of the way, the other two sections will go by much quicker. Okay, the next thing that's kind of to be expected here in this section is to talk about writing fractions in lowest terms. Okay, so writing fractions in lowest terms is what we want to be doing here. So we'll be given a fraction here, and sometimes in some questions, they're going to ask you, hey, can you write the fraction in its lowest form? So let's do a quick example. Let's do some quick examples here, and let's write the fraction in its lowest form. And we'll talk about what that means. All right, so let's go with this. We have 6 over 18, okay? And we want to go ahead and write it in terms of it in its lowest terms. Okay, so what do we mean by lowest terms? It means that essentially what we want to do is this. So the key here is to find common factors that we can divide out from both the numerator and denominator. Now, what do I mean by a common factor? All I mean is basically at the end of the day, I just want to find a factor. Again, just want to find a number that divides both 6 and 18. Okay? That's what I want to do. So, if I look at 6 and 18 here, all right, just to start with, is there any common factor, any number that can divide both 6 and 18? Okay, a 3 or 6, okay? Both are just fine. Okay, let's start off with 3, okay? I know 6 also works as well, so both are valid. Now, the point I'm going to make here is this, all right? At least for this first example. Now, the way it's going to work is it's going to work like this. Notice what it says here. Find the common factors we divide out but from both the numerator and denominator. Now, I'm going to present something here a little bit early, but it is very important for what we're going to be talking about later. This is a very important early concept that talks about a little bit about algebra. One of the most important things to understand in algebra, and even fractions here, is it's going to talk about the biggest key to all of algebra. Okay, so if it's like saying, okay, I need to understand, how algebra works. Well, this is kind of like a very good early example of that. The key to algebra, and you'll hear me say this repetitively, is basically, goes down to one word in my opinion, and that is the word balance. Balance is the most important thing when it comes to algebra or some mathematical calculations. All right, we have to be able to balance things out from the things that we see. Essentially, it is okay to, of course, divide out by 3 on the numerator and denominator, but this is also a reflective of a balance that we have to make. We can't make a unilateral decision, say, all right, I divide by 3 from the numerator, but not the denominator. Like, no, no, no. That's not how it works. Okay, we have to, again, balance things out. So one from the top and one from the bottom as well. That's what we have to do. And you'll notice that this will happen more and more and more as this semester progresses throughout every single one of these chapters. So you're going to see a lot more of this idea of balance in many different ways, shapes, and forms. Okay, so don't be surprised that you see this, over and over and over again in some form or fashion. So just go back and, think about what I've just said here. Balance is really one of the biggest keys into helping you out here in this class, okay? What you take away from one, sometimes you got to take away from the other. All right. Now, in this case here, we got 2 on the top, 6 divided by 3. That's what we on the numerator. 18 divided by 3, which is 6 here on the denominator. So if we have, now we just have to ask the question, do we have any other common factors? 2 over 6, do we have any other common factors? Again, you can repeat this process as many times as possible. Okay, 2. That's correct. They're both even numbers, so we could take 2. That's right. And so here we get here we get 1/3 is our answer here, and this is as far as we can go. Let's put a note here. All right, repeat the process as much as you can. 1 over 3, that's technically where we stop, and that's going to be your final answer for that problem. All right. And again, you could have picked 6, and then 6 would have gotten you the same result. But I wanted to also show you that you could do it in multiple steps as opposed to one step if you're not sure. So I give kind of the out here. It's like, okay, there's more than one way to do the problem to achieve the same result. You can start with 3, then you have to do 2. Or you could just do 6 straight up, and then you'll get the same answer regardless. Okay. How about this one here? Let's look at this one. How about this one here? 15 over 36. What is a common factor we can divide out by in both the numerator and denominator? All right, 3 is correct. Very good. So we'll divide by 3 here. All right. So here we're going to get 5 over 12. Okay. And there you go. That's it. 5 over 12. Simple dimple. All righty. Any questions so far? All right. Yeah, let me check that real fast. Okay. All right. Might look at those later, I guess. All right. Yep. Now, there are a couple of other things here that I do want to kind of mention outside of writing the fraction lowest terms. They also have like a kind of a comparison one here, which one's larger. You can kind of determine that there. Let's take a look at a question here about which is larger. So I'm just going to do a quick one here. This one isn't too bad. Okay. So we have to determine which one is larger. Is it going to be 5/6 or is it going to be 7/8? All right, so 5/6 or 7/8, which one is larger? Okay, probably should have put an or in between. That'd be helpful. All right, 5, 6, or 7 eighths. Which one is bigger? All right. So we look at both of these and we say, all right, it's kind of hard to determine which one is which. I mean, both of them are pretty close to 1. We have 5 over 6 and 7 over 8. Okay, both are, like I said, but they're pretty close. All right, so one of the things that we're going to be doing here is, again, sometimes what is going to be important is to determine which one is larger, and this is just for a little preview here. To determine which one is larger, hey, what is that? What we need to do is we need to get both denominators to be the same so we can compare the numerators. Okay. So if we're trying to determine which one is larger, if we can get both denominators to be the same, then we can compare the numerators, and then whichever numerator is bigger, then that's going to be our winner. And we'll take a look at this more in adding and subtracting, but I'm going to do this one out at the very least, and I can change actually 5 over 6 to, let's see here, 20 over 24. So I'm going to use 24 as my denominator of choice. And then I can change this one here. 7 over 8 can actually change over to 21 over 24. Okay, so these are actually equivalent. So as we can see here, which one is larger? Well, the answer is going to be 7 eighths. All right, that's going to be your winner. And we'll talk about how we actually got to that point of 7 eighths a little bit later on. But again, used again, probably if you've heard of it already, then common denominator. Shouldn't be anything brand new in terms of how we actually approach those problems. Okay, questions about that so far? Hopefully that wasn't too bad. Okay, let's take a good look here. You can again do this on the calculator if you like as well. You could do 5 divided by 6 and 7 divided by 8. You can compare those decimals if you want. That's also another way if you're just talking about larger. But I just wanted to showcase the same denominator there. We'll see how we can find those. Okay. In any case, let's take a look at some problems here from the book. All right, so let's look at some applications. Okay. Applications never hurt anybody. All right. So let's take a good look here at number 5. Okay. So number 5 says, is it possible to have a 7/8 inch pipe with an inside diameter of 29 over 32? So 29 32nds of an inch. So a 7/8 of a pipe, is it possible to have an inside diameter of 29 32nds? Okay, so what we want to do here is we want to see if 7/8 of a pipe is yay big, okay, as it says in the picture, and does 29 over 32 fit inside of that 7/8 inch of a diameter of a pipe? Okay, so let's find out. What we need to have happen is 29 over 32 needs to be less than that of 7 over 8. So let's find out what 7 over 8 is in terms of 32nds of an inch. Okay. Now let's go back to my previous point here. Let's put this in the same, using the same denominator here. So 8 times what is equal to 32? Let's multiply 8 by something to get 32. 8 times what equals 32? Okay, that's correct. 8 times 4 is 32, right? But remember what we talked about here. We talked about the word balance. So because we talked about the word balance, I just can't multiply the bottom by 4. I'm going to need to do the same here at the top as well. Balance here, by far and away, the most important thing we're going to learn here. So if we convert this, we got 32 on the bottom. That's exactly what we wanted. Now we got 7 times 4, which is what? All right, 28. So the question is, can a 29 over 32, 29 32nds of an inch inside diameter exist in this pipe? The answer is no. Okay, 29 over 32 is just too big for a pipe that has a diameter of 7/8. Okay, um, questions about that problem there? Okay, all right, let's look at, okay, this one's a good one here. So this is a very good problem here, and I'm going to go ahead and highlight this one here. If I can get this to work out, that is. So I'm going to try my best to get this to work out. Okay, so I want you to take a good look here at number 9. Okay, number 9. Before it can be used, a 12-ounce container of liquid fertilizer must be mixed with 48 ounces of water. What fraction of fertilizer is in the final mixture? Has anybody got an answer for me here for this one? What fraction of fertilizer is in the final mixture? 1/4, okay. Anybody else? A quarter, okay. Anybody else got an answer? A quarter? Anybody else? No. All right. Well, let's go ahead and take a look here. So the answer is going to be not a quarter. All right. That is the incorrect answer here. It is not 1/4. This is one of those problems, is why I highlight this problem here in particular. Read the problem very carefully. All right, so this is one of those that you got to be reading very, very carefully in order to get this one down. Let me read this again, okay? And now this will highlight why this is not a quarter if you listen carefully. Before it can be used, a 12-ounce container of liquid fertilizer must be mixed with 48 ounces of water. What fraction of fertilizer is in the final mixture? So the final mixture, right? Let's ask this question here. How many ounces of this mixture do we have? So after we mix it all together, So I'm just talking total, a total amount of ounces here. I know I have 12 ounces of the liquid fertilizer. That's definitely true. Totally agree. 60. Yes. That's the more important part here, actually. We know that we have 12 ounces of fertilizer, so that part, no problem, okay? That's given to us right away. But what you have to understand is that the subtlety behind the wording here is what actually makes this problem a little bit more difficult to get. So let's show that off here in just a second here. Let me make this a bit smaller. Go. Ah, why? Why have you done things? All right. So to kind of show off the subtlety for this, we're taking 12, that's the number of ounces, but then we actually have 12 plus 48 ounces of the mixture that we just kind of threw together. So we actually have 60 here. So now I have 12 out of 60, not 12 out of 48. That was the biggest difference here. So again, the wording is subtle, but it does play a very big role. Now, if I reduce 12 over 60, what would that be? 1/5, that's correct. So again, we could divide this by 12. Actually, I don't know why I did that. So we can divide by 12, we divide this by 12, and we get 1 over 5. Okay. Any questions about that one? Okay. So that was kind of like the more, that was kind of like the important parts there that I did want to focus on here in this first section anyway. All right, so this is kind of like, just kind of getting used to how it works, okay? Again, some parts here have that subtlety, so I wanted to kind of highlight and say, all right, here you go. Okay. That's nice. All right, question, do you guys want to take a break or should we keep going? Do you guys want to take a break or keep going there? Okay. All right, we can keep going. That's perfectly fine. Okay, let's keep going then. Democratic choices. All right. Majorities rules. All right, so we're going to go with that. All right. Okay, so that was the first section there. No problemero. All right. So let's go ahead and keep going here to the very next section, which is section 2.2. Okay, so what is section 2.2? Okay, so section 2.2 has stuff to do with, in this case, multiplication of fractions. Okay, now multiplication of fractions, at least the concept here, is really, really super simple. Like, it doesn't require any effort. But at least the trick behind it is, it can be a little bit tough. So let's say we had two fractions, a over b and c over d. So here we're going to get A times C, A times C, hello. A times C over B times D. Okay, so again, we multiply straight across, and we're able to get an answer for that without too much trouble. Okay, so that's the rule that we have there. Easy peasy lemon squeezy. But there is a big key to multiplying fractions here, at the very least. Okay, and we'll talk about that. So let's do that right now. Yes, I totally forgot to ask. I'm just going to ask this in the chat real quick, if anybody has a graphing calculator. I'm just going to ask here, no? Okay. A 36x would be okay, yeah. That's fine. I don't mind if you have a graphing calculator. I just want to see if you guys actually have one. Then I can go through like a separate process there. Yeah, you could have like an 83, 84, and I wouldn't care. So now the reason why I asked that is because I forgot to mention here from the first section is that using like a graphing calculator or even the 36X Pro, you could do fractions on the graphing calculator or whatnot, and it will reduce fractions for you. So if you say, hey, I got a 36X Pro or something like that, and I need to reduce fractions, you could literally, like on mine, I have the fancy schmancy one because, of course, I teach a bunch of classes, but um, I could teach like, again, I could go 4 over 6, for example, just like this. And we already know what this is, 4 over 6. Okay, but I can actually reduce this as a fraction here. I hit the math key on my thing. I hit the fraction key. You might have this on your 36X Pro. If it doesn't do it for you already, it should. You had to go to fraction and then hit enter. And then you could take a look here on my graphing calculator. At the very least, I know this is a little hard to see, but there you go. You see 2/3 on my calculator there for 4 over 6. So it does. If you have like a 36X, that's actually super handy to have. Again, you don't have to like go through a lot of motions to reduce fractions down. So I just want to show you shortcut methods of which to kind of help yourself out there a little bit. So I don't think a 36X Pro is a lot of money. So um, I think it's like, I don't know, how much did yours cost? Or I don't know if you got it for free, Jasmine. So I know it's not a lot of money. Not like the 83, 84, just like $100 or something, but you don't have to get that. 36X Pro is good in the shop as well. So yeah, $16. Yeah, such a great calculator for $16. So if you're in the shop or something like that and you're using it for practical purposes, it's super handy to have that. Like the phone is okay. The problem with the phone is it's a little unwieldy to use to push buttons on, especially when you also use the phone as your calling device. So it's like I'm trying to text and call at the same time of entering in numbers in a calculator. And you're like, yeah. Okay. Now, let's at least talk about, well, what are we talking about here when it comes to multiplying here? What's the trick into multiplying two fractions together to at least get things down? All right, so the trick is fairly simple here for multiplication of fractions, is basically to reduce before we multiply straight across. Okay? So that's what we want to do here. We want to reduce before we multiply straight across. That's going to be the most important thing here in this when it comes to multiplying two fractions together. So let's take a look at some examples of multiplication, and we'll see exactly how to do it. All right, and we're going to go right away into, maybe not the concept per se, but we're going to go right away into application. So let's do that. Okay. Okay, so let's look at this first one here. I'll look at, which one do I want to do? Sure. We'll do this first carpentry one here. Okay. Okay, so what length of a 2x4 material will be required to make 6 bench legs, each 28 and a quarter inches long? Okay, so we're trying to make 6 bench legs, each one to be 28 and a quarter inches long. All right, so let's take a look at this problem here. Let's do this one out. Okay, so in this particular case here, what we want to do is we have 6 bench legs here. We have 6 times 28 and a quarter. Okay, we're going to figure out how long this is going to be. All right, how much material we need in order to get this to work out. Okay, now the first thing that we're going to do here is first we're going to make a one note here that is fairly important. Okay, and that is of course 6. So as you can see here for 6, a 6 can be rewritten here as, let's put a note here. Note. Whole numbers can be rewritten as so the whole number over 1. So you'll see me do this a little bit often here. So you could be written as the whole number over 1. So i.e., what does that mean here in this case? That just basically means that I take that whole number of 6 and I just rewrite it as 6 over 1. Now, we're going to go ahead and take a look here at 28 and a quarter. Let's convert that into an improper fraction. So again, let's put this here. Okay, so convert all mixed numbers into improper fractions before you do any operation. And then the last note here, I'm going to put here note number 3. Convert back to a mixed number if necessary. In some cases, it may not be necessary. It just, most of the time in these problems, they'll ask you for a mixed number again. So, okay. How about 28 and a fourth? What would that be as an improper fraction? Can anybody tell me? 28 and a fourth as an improper fraction. 113 over 4. Okay, good. Okay, again, to get that, you get 28 times 4 plus 1 over 4. Okay, so just to showcase how we got that. Now, we're going to reduce before we multiply. And the reason why we do this is because, as you can see here, 6 times 113 is a pretty ugly number. Okay, it's not a very nice number, mind you. It's a pretty large number. So if we can reduce that number down as far as we possibly can, it'll make it a bit easier at the end once we have to put it all together again. All right. So we want to look here is to reduce. In this case here, we want to find a common factor from one number on the top and one number on the bottom. Okay. So we just have to pick a pair of numbers here. One number on the top, one number on the bottom. So one number in the numerator, one number in the denominator. So what two numbers have something in common that we can go ahead and divide out? Jeez. What pair of numbers here have something in common that we can divide out? Six and four is correct. Okay, what can we divide from 6 and 4? What does 6 and 4? What's its common factor? What do 6 and 4 have in common? 2. Right. So all we're going to do here is we're going to divide the top number here, the 6, by 2. We'll also divide this number by 2 as well. So 6 divided by 2, that'll be a 3. 4 divided by 2 will turn out to be 2. That's all we're doing here is just seeing if we can reduce things down. Now, unfortunately, this is as far as we can go for reduction because 2 doesn't go into 3 or 113. So now we'll multiply straight across. So here at the top, we're going to get 339 over 2. And now we want to convert that into a mixed number. So what is that going to be at the end of the day? $339 over 2. What's that as a mixed number there? You could use your calculator for this, so that's fine. 169 and a half? Okay, good. Yeah, you could definitely use your calculator for a lot of these. So again, if you need to, not sure, you can always convert it back. So 169 and a half is the correct answer. Good. All right. Okay, questions so far? No. Okay. Let's do another problem here. Where was that again? Okay, yeah, we have to do that one. So, all right, that's fine. Yeah, that's kind of weird, actually. Where is this? There it is. Okay. There it is. All right. Okay. All right. Let's take a look at this next one here. How long will it take to machine 45 pins if each pin requires 6 3/4 minutes? Allow 1 minute per pin for placing stock in the lathe. All right, so you're trying to machine 45 pins and each pin requires 6 3/4 minutes. Okay, can anybody tell me how you would set this problem up? How would we set this particular problem up here? So let's talk about the setup here. How do we set up this problem? If you're not sure, just tell me you're not sure. That's okay. Not sure? Okay, that's fine. 45 times 6 3/4. Okay, I'll certainly take that. That's true. Let's go ahead and do that. So let's do that right now. Okay, so we'll do 45 times 6 3/4. Now again, we're just going to convert here. So we're going to get 45 over 1. How about 6 3/4? That's okay if you're not sure. If you're not sure, that's fine. That's that's the part of the learning process there. So that's why we're here to learn and get these down. Okay, so if it's 6 3/4 here, what's 6 3/4 in terms of an improper fraction? So 6 3/4 is an improper fraction. 27 over 4. Okay, very good. Okay, so we're going to have 27 over 4, like so. Okay. Does everybody see how we got that improper fraction? Are there any questions about that real fast? I hope that was, any questions about the conversion there? Okay. I just want to be sure that at least you got that conversion down. Fine. No questions. Okay. Fine. No problemo. All right. So we take a look here and see if we can reduce anything down beforehand. And 45 and 4, do they go into each other? No, unfortunately they do not. 45 and 4 don't have anything in common, sadly. They're not even, or they can't. 4 doesn't go into 45 either. So we're kind of out of luck there. So we're going to need to multiply straight across here. And again, this is pretty much calculator time after this. So we have 45 times 27. So that's going to be 1215. Oh, actually, let me show this up here. Yeah. So what we're going to have here, again, we do 45 times 27 over 1 times 4. So here we get 1215 over 4. And all we have to do here is convert 1215 over 4 into a mixed number. So can anybody tell me what's 1215 over 4 as a mixed number? Again, you can use your calculator for this. I highly encourage it. Okay, 303. All right, very good. 303 and 3/4. Okay. Now, there is one more part to this problem here. So look at it carefully here. What else do I need to add into this problem here? What else needs to be added into this problem, you think? Not the units. You're missing. Yeah, allow one for each pin. We'll add the units here for sure. But if you take a look at the last part there, we have to allow a minute per pin for placing the stock in the lathe. So we'll need to add in an extra 45 minutes for the 45 pins that we are making here. So again, just be careful about those last little extra tidbits there that we're going to have to kind of add in. Adding 45 here is really easy. Just add those nice whole numbers together. 348 and 3/4 minutes is what we get here for this problem. Okay? Okay, good. Are there any questions about that problem before we move on? Nope. Again, if you need to stop and ask me questions, please feel free to do so, okay? Okay. Let's look at the next one here. Okay. Okay, so let's look at the this will be the last example here for this section. All right. 26. The center to center distance. Oh, how do I convert the question into the problem? Are you talking about the last example there, Brenton? Let me go back here. There we go. So you're talking about the yes. Are you talking about the 1215 over 4 being 303 and 3/4, or are you just talking about this first part here, the 45 times the 6 and 3/4? I just want to know. I just want to clue in on which one you want to kind of focus on. The first part? Okay. So in the problem here specifically, where are we? Let me go back for just a second here. So in the problem here specifically, it says that it says how long will it take to machine 45 pins? Now each pin requires 6 3/4 minutes. So that means it's going to require me to take 6 3/4 minutes to finish one pin when I complete it on the lathe. Okay, and I'm making 45 of these. So what I do know is that I'm going to take 45 times the 6 3/4 minutes that I'm going to take to make each one of these individual pins. Okay, so that's where I get this first part from. Now, I rewrote this problem here because we can rewrite 45 can be rewritten as 45 over 1. So that was the note that I put right here, was whole numbers can be rewritten as the whole number over 1. So I did that first part there. Then 6 3/4 was again 6 times 4 plus 3, okay, over 4. So that's 24 plus 3 over 4. So that's where I got the 27 over 4 from. Again, I always look to see if I can reduce. Unfortunately, in this problem, we weren't able to, but once we put it together as 1215 over 4, we converted to 303 and 3/4, and then added the extra 45 minutes to machine the parts in between. So that's essentially what we have there to kind of put together that first part. I hope that answers that question. No problem. I thank you too. All right, very good. So good. All right. Yes. All right, let's look at number 26. All right, so this will be the last one here, 26. The center to center distance between consecutive holes in a strip of metal is 5/16 of an inch. What is the total distance x between the first and last centers as shown in the figure? Okay, so 5/16 of an inch, as you can see here, and we want to find the distance from the first hole to the last hole. So let's see how many holes we have in between. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 holes in between the first one and the last one here. So what we're going to have here is we're going to have specifically, so we're going to have 8 times 5/16. Okay, we will rewrite the 8 as, again, 8/1. Now the question is, can we reduce anything down? Are we allowed to reduce anything down here? Okay, what can we reduce? The 8 and the 16. Okay, perfect. What can we divide by? You're seeing an odd number of holes. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, there are an odd number of holes. We could divide by 2. Okay, that's true. So we get 4 here. 8 divided by 2, 16 divided by 2, 8. Can we still reduce down? Jasmine, you're correct. There are an odd number of holes in there. Yes, we can continue to reduce. What can we divide by now? 4 and 8 go together. So we can divide by 4. That's correct. So this can happen multiple times if necessary. That's certainly plausible. Just because you divide out once doesn't mean you're technically done. So we get 2 here. So we get 1/1 times 5/2. So we talk, this is going to be 2.5. So if you do this out, 2.5 will be your answer for that. Now, to answer your question there, Jasmine, okay, no, that's fine. So I start, basically, let's read the problem here once again, okay, Jasmine? So it says, the total distance between the first and last centers as shown in the figure. So I just started here, and I just counted the number of differences here. So we say 1, so we go 1, 2, 3, 4, 5, 6, 7, and 8. So there are 9 holes in the picture, but there's only 8 holes between the first one and the last one, right? The 9th hole and the first hole. So there'd be 8 holes in between. Okay. Okay. Yeah, so it's a little tricky because you're thinking that, oh, it's got to be 9, but no, it's actually 8 between. So, yeah. All right. Okay, any questions over multiplication? Any questions at all over multiplication? No? 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 Okay, that's That's fine. Yes, 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 no, yes. All right. All right, next. All right, let's talk about the last section here for today. You're probably like, finally, made it. Like, yep. Okay, that's fair. Okay, so the last section I want to go over here today is division of fractions. Okay. So division of fractions here, we have a rule for that as well. So let's go ahead and write down that rule here. Apologies, they're doing some landscaping and mowing the grass outside, so if you hear that, sorry about that. So let's say we have A over B divided by C over D. Okay. Now, one of the things that we're going to do here specifically is to do A over B divided by C over D. Essentially, we don't want to divide straight across. That's not how it works for division of fractions. Instead, what is easier than division is multiplication. So we're going to change this into a multiplication problem. What we'll do here is we'll keep the first fraction the same, and then we'll multiply by the flip of the second fraction here, which will be D over C. So again, we're going to get A times D over B times C. So this basically, let's talk about the big key here. Do we divide the top and bottom numbers separately in the previous problem? Let me see. Oh, yes, this is not. Yes, thank you. So you're talking the 8 and the 16 here. I think you're saying yes. But remember, one of the important parts here, Brenton, is that if we had started with this, okay, then you divide each of these separately, but they're just by the same number because they share the same common factor. So if I went ahead and I divided this by 8, I have to balance it out by dividing another number by 8. And because I know I'm going to get a nice answer out of this, again, a very nice clean number because they both say share a common factor of 8, I can just do 8 divided by 8, which is 1, and 16 divided by 8, which is 2. So yes, they're separate. They divide the numbers separately, but we're dividing by the same number on both the top and the bottom here to keep our balance. So remember, it just kind of goes back to talking about balance here when we talk about algebra. We're still doing the same thing here in this case as well. So to answer your question, yes, just remember you're dividing by the same number here with two numbers that have a common factor in between. So as long as they have something in common, you can divide that out between both of those numbers there, as long as one is on the top and one is on the bottom. So in this case here, this is multiply here in the middle. So this is times, not divide. I think you got that backwards there. So this is times here. Division is what we're talking about right now, but this is just straight up multiplication. So this is 1 over 1 times 5 over 2, and then you multiply straight across. Okay, what about 1 over 1 divided by 5 over 2? Okay, so what if I did that? Okay, that's a fair question. So let's say I did 1 divided by 5 over 2. Let's focus on that here for just a second. So let's take that as a scenario question. I think that's fair. Let's go ahead and take a look at that. So let's say this is our problem here. 1 divided by 5 over 2. Okay. Now, one of the important things that I'll stress here is that let's talk about the key here behind this process, okay? And then hopefully it'll make a little bit more sense about what we're going to be doing here. So the big key here is, as you can see here, we have a division, but we want to change it up to multiplication, but with the consequence. So again, we change the division to multiplication. Division to multiplication, and flip the second fraction. This is also what you called the reciprocal, aka the reciprocal. I could never spell this word, and I never get it right, but it's called the reciprocal. Yeah. Okay. So what I'm going to do here is, in this particular instance, is if I have 1 divided by 5 over 2, I'm going to take, say, 1 over 1, and I'll instead, I just, and I flip just the second fraction. So notice here I flip just the second fraction here, okay? So that's why this suddenly became from C over D to D over C. That's the consequence of changing it over to a multiplication problem here. Uh, so now we're going to multiply that by the flip of the second fraction, which is 2 over 5. And now I just multiply straight across after that. So here we get, let's see, what do we get? Yeah, we get 2/5 here. Okay. All right. So as you can see here, once we change it over to a multiplication, we go ahead and multiply straight across, and then we're done. So we make the adjustment there for division, all right, by changing it back to multiplication. We do not divide straight across. Okay, so let's at least get that. I'll make that as a note there, so that way it clears up any confusion. Note we never divide straight across. So this should never happen, okay? We do not divide straight across. Again, the reason is we want to put it into a context we do understand, so we change it over to multiplication because the rule for that is very straightforward. The consequence being flipping that second fraction in order to do so. Okay, cool. That's what it's there for. So I'm here to help with, just to help you understand. That's what it's. That's exactly why I'm here. Okay, let's take a good look here at a problem, a few word problems actually, in this section that we'll be encountering later on, for certain. Okay. All right. Let's take a good look at this first one here. All right. So let's look at number 2. Number 2 says, if a 1/4 of an inch on a drawing represents 1 foot, then 3.5 inches on on the drawing will represent how many feet. So again, if you're making like a blueprint or let's say an architectural design, then obviously you can't make a full scale size of what it should look like. You obviously have to put a representation of how many feet, say, a room is or the like. So if we take a look here, a quarter of an inch represents 1 foot. So this dimension here is 3.5 inches on the drawing. So what do you think we could do here? Well, we know that every quarter of an inch is 1 foot. So since we have 3.5 inches in this particular instance, we're going to take 3.5 inches and find out how many quarter inches that's going to be. So we're going to take 3.5 and divide it by a quarter. Okay. This will allow us to find out how many quarter inches that we actually have here in this given problem. Now, in order to do this appropriately, the first thing that we're going to do here is remember to go ahead and change your mixed numbers into improper fractions. So again, note 2. Okay. Remember, this is why I kind of stressed in the first section here why I said, oh yeah, you know what, you want to convert these into mixed numbers. These mixed numbers into improper fractions. This is again another big reason why, because the calculations make a ton more sense if we go ahead and do so before anything else. So let's take a look here at, I don't want to do that. Let's look at 3.5. What's 3.5 as a improper fraction? What's 3.5 as an improper fraction? 7/2. Good. So we get 7 over 2. Again, to get that here, once again, we did 3 times 2 plus 1 plus 1 here. And then over 2. Okay. And we divide that by 1 over 4. Okay. So what happens next? We got 7 over 2 times 7 over 2 divided, excuse me, by 1 over 4. What should that look like? If I divide those two fractions, what should it look like? Okay. So if we flip this second fraction, so let's take a look at the second fraction here, okay? If we flip this second fraction, what does this second fraction flip to? Okay, so first flip this second fraction. So we're going to keep the first fraction the same. So the first fraction of 7 over 2 doesn't change. The second fraction is going to flip. That's going to flip to 4 over 1. So we're going to just flip the numbers, put them in the, put the denominator in the numerator in denominator. And all we have to do is change that division now to multiplication, okay? Using the rule that we have here for division of fractions, okay? And now we can go ahead and see if we can reduce things down once again. Why flip? Because we're dividing here. When you divide, you flip. So that's the rule we have to use here. Take a look at our key here. Key here is to change the division to multiplication and flip the second fraction. Okay, so that's going to be the process. All right, anytime you divide fractions, this will always be the case. You flip the second fraction only, change to multiplication. It's easier to do multiplication because you can't directly do division when it comes to fractions. I could explain it in more detail. It would be the best way I can think about it is Okay. Here's the best way that I can think about it. Let's say you had a pizza. Okay. Let's say you had a pizza here. Okay. Let's say you cut it in half. Okay. So you cut that pizza in half. You know, half could go to you, half could go to your friend or whatever, right? Okay. Well, let's say I ask you the question. Let's say I ask you the question. So how many halves do you have? That's kind of weird. But how many halves do you have there? That's my question to you. How many halves do you actually have? You have two, correct? You got one half, you got two halves. In fact, what I've just shown you here is 1 divided by 1/2. This is the same question. 1 divided by a half. How many halves do you have? Well, if I'm taking one pizza and divide it by half, how many halves do I have? Well, that's actually 1 times 2 over 1, which equals 2. I know it's a little complicated, but that's exactly what we're doing here. So it's a little counterintuitive at times. It's just that's the way we kind of do that there. Okay, now we're going to reduce something down here. Okay, cool. That's all I asked for. All right, so we're going to reduce here by 2. Okay, so we're going to divide by 2 for 4 and 2 here. So this becomes 1. This becomes 2. So here we're going to get, let me go ahead and erase this out because I'm going to need the space. Wow, that looks worse than what I left it. Okay, nice. Okay, so I'm going to have 7 over 1 times 2 over 1. So that's going to be 7 times 2 over 1 times 1. So that equals 14 over 1, which will just be plain 14. Okay, so 14. So 14 is going to be our final answer for this problem. Okay, questions about that? Hopefully that's not too bad there. So, yeah, it'd be 14 feet for that. Okay. Yeah, that's good. Okay. All right. The next one here will also be important as well, so it'll be an important word problem here. So let's talk about that one. Okay. All right. So this one here can be a little tricky, so we're going to take a look at this carefully. All right, so number 9. How many pieces 6¼ inches long can be cut from 35 metal rods that are each 40 inches long? Okay. So each one of these metal rods is 40 inches long. We have 35 of them, and we want to cut pieces that are 6¼ inches long at the end of the day. That's what we're after, okay? So nothing crazy, nothing too bad. Okay, so what we're going to do is we're going to take the 40 inches, okay? Because each rod is 40 inches, and we're going to see how many pieces that we can cut here from the 6¼ inches long from this. And I'll need to describe that. So I just want to talk about one subtlety in this problem that people often get wrong. So now let me go ahead and describe what's going on here. Okay. So let me talk about the reason why I'm actually dividing 40 divided by 6 1/4 in this problem. Some people would look at this problem here, and actually in this case, order kind of matters, kind of. Now, some people would say, well, let's see how many inches of steel bar that we actually have. Okay. And you would say, okay, take the 35 times the 40, and then that's how much, that's how much steel, that's how much of these metal rods, this metal rod that we have here. Now, here's the problem. The problem is that each of the metal rods is a separate individual piece. You're not welding all 35 pieces together into one long line. Instead, you have 35 of these metal rods that are completely separate, in which case you're making these particular cuts. Okay, so one of the things that's kind of important here, at least in the context of this problem, is that understanding the realistic context is just as important. Okay, so we do not multiply 35 times 40 first, since the rods are separate. So that's why we're doing 40 divided by 6 1/4 as opposed to the other way around. We're going to figure out how many pieces we get from each particular rod, and then multiply that by 35, and then we're going to get our answer for that. So it's little subtle things like that that you kind of have to be a little careful about. So here we're going to get 40 over 1. What are we going to have here? We got 40 divided by 6 1/4. What's 6 1/4 as a improper fraction? (25 over 4). That's correct. Very nice. 6 times 4 plus 1 over 4. So we're going to divide that by 25 over 4. Okay, what comes next? How should I rewrite this problem? Okay, very good. That's right. So now we're going to rewrite it in terms of a multiplication problem. So we have 40 over 1 times 4 over 25. Okay. All right, so we changed it to a multiplication. Now we can reduce. So now we can reduce here. So what can we reduce here? Does 40 go into 25? Because again, we pick one number on the top, one number on the bottom. (40) doesn't go in it. Okay, there's no common factor between 40 and 25? All right, 5. It was like, oh, wait, what? 5? All right, we would Booker T that stuff. 5 time, 5 time, 5 time, 5 time. All right, so we divide by 5 here. We have 40 divided by 5 and 25 divided by 5. 40 divided by 5 is 8. 25 divided by 5 is 5. Okay. So do we have anything else? Nope. Okay. So let's take a look at what we have here. We have 8 over 1 times 4 over 5. So now we'll multiply here straight across. 8 times 4 over 1 times 5. Okay. Now what's 32 over 5 as a mixed number there? So we got 32 over 5. But what's that as a mixed number? Very good. The answer indeed is 6 and 2/5. That's what 32 over 5 is. Again, that's going to be, again, how many times does 5 go into 32? 6 times with a, oops, I meant to put 30 here. So we got a remainder of 2 there. So 6 and 2/5 is how we can determine that. Now, let's think of it this way. All right. Let's think of it this way. We have 6 and 2/5 pieces. Okay, so remember that's the units here. 6 and 2/5 pieces that we can cut. Does this make any sense? Can I cut 6 and 2/5 pieces? No. Okay. Okay, so this is the other half of the problem that, again, you have to be very careful about. Remember the context that we're working over, okay? So in this case here, let's go ahead and put this in a little text bubble as well. We're going to say 6 and 2/5 is 6, all right? Since 2/5 of a piece is not realistic. Okay, so since 2/5 of a piece is not realistic here, sorry about that. I didn't mean to do that. I don't know how to get that back. Shoot. Arr! I always have issues with this thing. All right. So 6 and 2/5 is 6 since 2/5. Okay, there we go. All right, there we are. Okay, so what we're actually going to do here at the end of the problem is we're going to go ahead and take the 6 here, and we'll now multiply it by the 35, since we can only get 6 pieces per rod. So we're going to take the 6 times the 35. We go ahead and put that together there. We're going to get 210 pieces in this particular instance. Okay. Are there any questions about that? Obviously, there are a few little tidbits here that, of course, can be a little tough. But, oh, excuse me, man, shoot. But we're going to have to at least understand about why we're choosing the things that we are here in these problems. So Yeah, so the 2/5 would be extra, but it doesn't make any sense. We need one full piece, right? So we need one piece instead of 2/5 of a piece. Yeah, so 2/5 would be like a waste piece, essentially. So we don't want a waste piece, we want whole pieces, right? That's the only thing that really matters. We know that each one is going to be, say, 6¼ inches. That part is true. But 2/5 of a piece doesn't make any sense since we only want whole pieces at the end of the day. So that's why we rounded to 6 here, because even if this was 7/8, I would still round to 6 because I need whole pieces at the end of the day. I would take it to the boss and be like, yeah, I don't need 7/8 of a piece, I need a whole one. So I can't use this, bye. So yeah, so essentially that'd be waste. Any other questions? Again, you can ask me whatever. Okay, so if there are no more questions here, I'm going to go ahead and end off here for today. This is the 3 sections I want to kind of complete. We've been at it for about a couple hours now, so I think that should be plenty of time for you guys. Okay, all right, next time we're going to finish up chapter 2 here. We're going to talk about adding and subtracting of fractions. That requires a little bit more time, in my opinion. So I don't want to be like overwhelming you with too much information. Any work today? So if you want to kind of keep up with the work here, we did sections 2.1, 2.1 to 2.3 here today. Um, so yeah, no problem, Bren. Um, so sections 2.1 to 2.3, if you're keeping up with the homework there. Again, the homework's not due until I announce, say, the test or something like that. So you have plenty of time of which to finish. So there's no hard due dates there. No, we do not meet Friday. We just meet Mondays and Wednesdays. So we'll be meeting again next Monday here at 10 o'clock. Okay. All right. Well, I want to thank you all very much for coming out to the stream here today. All right. Great job, everybody, here today. We're going to go over cover the last part of chapter 2. We'll start chapter 3 on Monday. All right. Okay, everybody. Have yourself. Can you email the notes? Sure, I can do that. That's not a problem. All right. Have yourself a great one. All right. Everybody take care of yourself, and we'll talk to you later. All right. Have a good one, everybody. All right. Bye.